All right, guys, welcome back yet again. We are going to continue our discussion of BGP. And in this topic, we're going to talk about iBGP. Well, we'll talk about a few things, but we're going to spend a little bit of time talking about iBGP full mesh. You know, each one of these BGP discussions are, you know, I wouldn't say quite extensive, but they do require a lot of in-depth discussion. So this will be probably about as long as our previous lesson. But we're going to focus primarily on our iBGP peers. I've modified our topology a little bit, and I'll upload this topology into the Google Drive for you guys after we're done. I've added another ASN 50. We've got an eBGP peering link between router 7 and router 8. And we've got our own ASN 100 that we're going to be using as a transit AS for the prefixes that are coming from Area 51 or ASN 51 and ASN 50. I don't actually have anything configured in this topology presently other than IP addresses, which I just finished. So we're going to be doing this configuration from scratch. Okay? All right. So we talked yesterday in our previous lesson about why, what were some of the peering requirements for iBGP versus eBGP. And iBGP requires a full mesh, or at least if you're not going to do a full mesh, you have to run some sort of confederation or route reflectors or some other method of disseminating routing information. All right. So we'll take a look at that. We're going to find out why iBGP would require a full mesh. We're also going to take a look at a couple of different configuration examples. What are some of the issues we can run into? We'll talk about the advantages of having an iBGP full mesh versus not having one, or what some of the disadvantages are of having one. That has to do primarily with the control plane and number of relationships that we would have to have, peering relationships we would have to have, and so on. You know, what can we do with regard to maybe combining a full mesh or even a partial mesh with a confederation or a route reflector, which would then provide us the ability to implement a partially meshed design. I'm going to talk about confederations and route reflectors a little bit. I'm not going to spend a lot of time getting into the configuration of those components in this lesson. I will introduce the concepts because we're going to have another lesson later on where we talk about primarily route reflectors. We don't spend a whole lot of time talking about confederations because they're not really used that much, but we will spend some time talking about route reflectors. Most cases, people are going to assume that you have to have a full mesh if you're running iBGP, and having that full mesh is necessary, but that's not always going to be the case. The basic problem state that we have to do, that we're dealing with in the beginning anyway, is that we need the full mesh based on what? It was what we discussed yesterday when we talked about one of the three major differences between iBGP and eBGP. And that had to do with how iBGP peers propagate routing information to other iBGP peers. In the case of iBGP, as a loop prevention technique, really one of the only loop prevention techniques that we have with iBGP, is that we cannot advertise prefixes learned from one iBGP peer to another iBGP peer. Okay? Now, this is what implies that we need a full mesh of peerings. Now, before I actually get into the configuration and the implementation, I want to go through some discussion of BGP, specifically iBGP, and talk about this from a scalable design element. We'll take some notes. I'll put those notes into the Google Drive as well. And then we're going to get into the actual configuration and the implementation, and then we'll wrap up our lessons by kind of taking a look at BGP databases and look at the view of the topology from different BGP peers and so on. All right. BGP, obviously we know, is typically going to be used to connect multiple connections to the internet. We're kind of simulating that in this particular topology. And it's used for very, very large domains. Now, in this domain, we're not really operating in a very large environment, but we can extrapolate some of the concepts that we're going to learn in this lesson to those large implementations, all right? And our focus, even though we're going to talk about scaling BGP from a lot of other perspectives in different lessons, our focus is to discuss the aspects of scaling in basic internal BGP design, where we have iBGP peers. Now, from the iBGP perspective, our focus is going to be on ASN 100, where we've got 4 routers that are linked together, creating this mesh, if you will, or converged topology, where we have multiple egress points from the AS to other prefixes that are learned from outside the AS. Now, if I was to take this topology and say I was to add this prefix here, let me grab a snippet of this real quick. If I was to take a prefix from AS51, for example, and advertise that into AS100 through the relationship between router 5 and router 4, I'm going to learn that route, say it's 172.16.57 or whatever it might be. I'm going to learn that route through my eBGP peering relationship, okay? Now that means that that route is then in turn going to be advertised to these peers because it is being learned through an eBGP process. However, R3 would not route or advertise that prefix to R1, and R2 would not advertise that prefix to R1 if we did not have a full mesh, because of the basic loop prevention techniques that we have within iBGP, which is the state that I'm not going to advertise a prefix that I learn through iBGP to another peer in my iBGP domain. So R3 and R2 might have that reachability information because R4 is then propagating an eBGP route to those peers. But this is a controlled mechanism, all right? Now, a full mesh of iBGP routers in this particular case would be needed because, like I said, we do not re-advertise routes learned via iBGP to other iBGP peers, all right? This is just part of the behavior of the BGP protocol that's used to prevent information from circulating between iBGP speakers in this routing information domain so that we prevent loops or cycling of that information between other peers. External BGP relies on autonomous system path prevention loops to prevent loops, the AS path attribute, if you will. We talked about that in our previous lesson. But there's no way to really tell whether a route is advertised through several different iBGP speakers. In this case is a loop because we don't really identify a separate AS path, right? We're using all the iBGP peers are in the same autonomous system. They don't need to add anything to the AS path attribute, so that means they're not going to re-advertise those routes learned via iBGP. Now, commonly, BGP is going to be used for multiple connections to the internet, to MPLS VPNs, MPLS mixed mode with IPsec VPNs, and so on. Because iBGP routers require a full mesh of peers, there is a scaling issue, and I'll mention this a little bit later on. I've got some numbers in my notes to kind of identify what the scaling issue is with iBGP. But it's that typical n to the n-1 or n times n-1 divided by 2 scaling factor that we use for peering relationships. So every peer would need the CPU, the memory, the bandwidth to handle updates and peer status for all the other routers within that autonomous system. It's not a hierarchical design, and it's not really cost effective to scale in a really, really large environment. Now, there are 2 alternatives outside of running an iBGP full mesh, and that is to configure either a route reflector or a confederation, okay? Now, like I said, I'm not going to get into the specifics of route reflectors and confederations, but I do want to introduce the concepts, even though we're not going to see them in the implementation in this case, because I want to, you know, the more times you hear about it, the the more likely it is that you're going to retain that information. So I do want to talk about essentially what some of the basic concepts are. All right. In a BGP environment, let's talk about a route reflector first. A route reflector is essentially an iBGP speaker that reflects or repeats different routes from iBGP peers to other iBGP peers. All right. So let's say, for example, I had a topology. We'll just draw a basic topology here, and we'll use this as our reference for this discussion. Let's just do this. So let's say that I have, this topology here. All right, and I've got essentially full connectivity between each of these peers. All these routers are in the same autonomous system number. What I would do is I would configure, rather than having to have a full peering relationship between all of these routers, I would configure, say, R1 and R2 as route reflectors. So these would be this would be route reflector, and this would be a route reflector as well. Okay? All right. And we'd actually use the command, and we'll see this command a little bit later on, but we would have like a neighbor, IP address, route reflector client. Now, to prevent loops, the route reflector adds something called an originator ID and a cluster list to the routes that it reflects between its iBGP speakers. It's kind of like an autonomous system path attribute, or a tag, if you will, that allows us to prevent those loops from occurring within the domain. All the configuration of the route reflector is actually done on the route reflector itself. The configuration identifies which iBGP peers are route reflector clients, and it's a relatively simple implementation. Like I said, we'll take a look at it a little bit later on. We're not going to implement it in our topology, but it's actually not a difficult configuration. Okay, implementing route reflectors is also something that you can do incrementally. So you could choose to maybe run a mixed mode environment where you have a full mesh of iBGP speakers in part of your domain, and then you decide to implement route reflectors in another part of your domain, for maybe optimal path selection in the full mesh, and then non-optimal, what we call cold potato routing, in the with the route reflector clients. Okay, each client router needs to be configured as a client on the route reflector, or on multiple route reflectors if you actually have a bunch of different route reflectors. Okay, most of the time, route reflector clients are going to peer only with route reflectors. In service provider networks, you might see this where you would actually extend this beyond just the clients themselves. The clients might also be provider edge devices, which would then peer with customer routers using eBGP. All right, and typically we're going to implement multiple route reflectors. Basically, what a route reflector client is any router that's peering with a route reflector. So in this topology here, we would essentially have two clusters of routers. We would have a cluster here, and we would have another cluster here of routers. And each of these routers, let me go ahead and put some labels on those. So R3, R4, R5, R6, these are going to be your route reflector clients. All right, and they're going to report their information. That's supposed to be a route reflector. There we go. They're going to report their information to the route reflectors. All right, so basically a route reflector client, in this case R3, R4, R5, and R6, is basically an iBGP router that receives and sends routes to most other iBGP speakers through that particular route reflector. The route reflector client doesn't actually really need any special configuration. other than maybe removing any kind of iBGP peering relationship that you had with other neighbors that were not the route reflector originally. So maybe if you had some peering relationship that was up here from router 3 and so on, you'd want to go ahead and remove that peering relationship because it's not necessary anymore in this particular case. All right. So the general concept of a route reflector is a fairly simple concept. A cluster is basically just a route reflector with its clients joined together. The route reflector receives the route reflector client routes, and then it propagates that on to the rest of the routers in the domain. All right. You can actually have clusters that overlap as well. We don't see that in this particular design, but you do have clusters that could potentially overlap as well. A non-client router, which would in this case would be, I guess, R7, the top router here. A non-client router is any route reflector iBGP peer that's not a route reflector client of that particular route reflector. So these would be essentially non-clients going from, let me use a different color here, going from here to here. That would be a non-client relationship. That would be a non-client relationship, and so on. All right, so they're not part of the cluster. We would just have a standard iBGP peering relationship between those peers. All right, now again, we'll take a look at the configuration of this in one of our future lessons, but I did want to introduce the concept. All right, now route reflectors, typically, they're going to be non-clients with regard to any other route reflectors in the network. So R1 and R2 are actually non-clients of each other as well. They still have to be fully iBGP meshed though with other non-clients. So route reflectors do allow us to reduce the meshing within the cluster, but all mesh links outside of the cluster have to be maintained on, in this example, router 1 and router 2. All right, so the route reflector clients then get their information from iBGP speakers outside of the cluster only through that particular route reflector. How many routers you decide to have in the cluster, how many route reflectors you decide to have in the design is entirely up to you. But keep in mind, there's a trade-off here. There's a trade-off between having full reachability information and being able to make the correct routing decisions versus control plane load and route processing and CPU load based on the number of iBGP peers that you have to have in the topology. All right. If a route reflector receives a route from a non-client, let's say R2 gets a route from R7, it essentially reflects that route to the route reflector clients, but not to the other non-clients. So because we have that relationship of route reflector client, which I would configure on R1 and R2, I would say neighbor R5 on R2 and neighbor R6 are route reflector clients, it negates that requirement that says iBGP speakers can't re-advertise routes to other iBGP speakers. All right, we have a question online from Mike. It says, wouldn't you want the two route reflectors in case of an outage? Absolutely, yes. You would definitely want the two route reflectors in case of an outage. And by the way, I've drawn these clusters as non-overlapping clusters, but most likely you'd want overlapping clusters for redundancy, right? So if router 2 fails, router 1 can still provide routing information to router 5 and router 6. I just didn't draw the topology in this particular case that way. And like I said, we'll get into that in more detail when we get into optimizing BGP in some of our future lessons. All right. If the route reflector receives the routes, well, it will actually, right? If it's going to have a direct peering relationship to a non-client, it will receive the route. The route reflector also sends the route into eBGP, which is, kind of normal behavior. We always repropagate routes to eBGP peers if we need to. and iBGP routes get repeated to all of those different eBGP peers. That's standard BGP behavior. All right. All right. If a route reflector receives a route from an eBGP peer, it's going to pass that route to all the route reflector clients and the non-clients like normal behavior, because there is no restriction from taking a route from eBGP and repropagating that routing information to other iBGP peers. There is, regardless of whether or not they're actually route reflector clients. If the route reflector receives a route from a route reflector client, it reflects that route to the other clients within the cluster and any of the non-clients. It also reflects the route out to eBGP peers if they exist. All right. Essentially, it's kind of like a designated router in OSPF, where the route reflector takes over the communication for the route reflector clients, passing all that information along, all the messages that would normally be transmitted during a direct peering session between the speakers, right? Also, route reflectors ignore split horizon, especially the design of iBGP and re-advertising routes that they receive from any other neighbor that they have configured when they're configured as a route reflector client. Ken has a question here. Does this drawing reflect eBGP or iBGP? Can it be either? This reflects iBGP, because you would never need to configure route reflectors with eBGP peering relationships, because there's no restriction on one eBGP peer from advertising prefixes to another eBGP peer. In the case of this design, what we're trying to do is say, rather than have to have R3, R4, R5, R6, if we weren't using route reflectors in this case, you would have to have peering relationships with each one of these routers, and then they would have to have peering relationships with all the other routers and so on. You get the idea. What we're trying to do is avoid that by creating these concentration points in the network where we can reflect the information. Again, we're not concerned about link information. We're concerned about network layer reachability information, advertising routes, not advertising links. Now, confederations could be another way to scale iBGP. It was actually the confederation was defined in RFC 5065, I believe. But I'm going to kind of step away from talking about confederations right now, because in most cases, if you have a situation where you don't want to run a full mesh of iBGP peers, most likely you're going to be implementing route reflector configurations anyway, and not confederations. So we're not going to talk specifically about the confederations in this case. I will talk about it, because you certainly have to be aware of that information before you get into the written test in the lab. But you know, from a practical use standpoint, it's not really that critical to understand. All right, we do need to know though, what is the result, or what is the potential result of combining maybe a full mesh with a confederation, or a full mesh with a route reflector. You know, in a sense, well, we wouldn't be running a full mesh in that case. We'd be running a partially meshed design. So it's something that we will build on, something we'll talk about. We could certainly spend hours and hours and hours and hours talking about all different kinds of design considerations. But my primary goal for you guys with this information is to understand usability. Why would I use a particular design, and so on. Okay, so let's take a look at our topology. Like I said, in this topology, I've pretty much removed all of the routing, and all we're going to see in this is basic link connectivity. So we don't really have any routing applied here. BGP has not been configured on any of the platforms, and we're going to start to kind of build out this topology by adding BGP to each of our peers, and then during that process, we'll be taking a look at iBGP summary and iBGP, and kind of looking at how these routers are making decisions on how they decide to route. All right. I'm also going to simulate diverse connections, and that's why I added this link, this 172.16.78 link, to simulate multiple service providers with a link between them, in this case router 8 and router 7. And AS100 is going to be used as a transit AS to be able to potentially route between AS51 and AS50 through AS100. Okay, so let's start with router 8, and all we're going to do is just a basic peering with router 1 and router 7. These are both eBGP peers. So let me go into my configuration tab here, and I'm just going to do a quick show IP interface brief exclude unassigned. All right, so these are the three interfaces that are configured on this router. 1 to 8 is router 18, subnet 18 is router 1 to 8, subnet 78 is router 7 to 8, and then we have our loopback. All right, so we'll start with router 8. Let's just go into our global configuration mode, router BGP 50, and let's do a neighbor. Router 1 is in AS100, router 7 is in AS51. So let's do a neighbor, and we're just going to do, rather than loopback peering here, we'll just do peering to the physical interface. All right, remote AS100. And let's go ahead and also send in our loopback as a route in BGP. All right, just to simulate some network that's going to be advertised into BGP. We're eventually going to add additional prefixes to be advertised, but we just need to be able to have some things that we can verify path selection and verify routing information. All right. We also need to go ahead and set up the neighbor for router 7. So let's do a neighbor 172.16.78.7 in this case, and that neighbor is in AS51. All right. So obviously, in order for us to be able to exchange information, we need to set up the peers on router 7 and router 8. I'm also going to actually set up the peering relationships on router 5. So going back to the diagram, router 7 we've done, or actually router 8 we've done. We need to do router 7 and router 1, and then we're also going to do router 5 as well in this case. Eventually we'll get to the point where we're setting up all of our peering relationships. This between router 5 and 7 will be an iBGP peer, and between router 1 and router 8 will be an eBGP peer. So let's start with router 1. Config T, do show IP interface brief, exclude unassigned. All right, router BGP 100, neighbor 172.16.18.8, remote AS 50. All right. I'm not going to do any of the peering relationships to the iBGP peers just yet. I'm just going to kind of focus on the edge routers for now. All right. If I do a show IP BGP summary, I should see that I'm learning that prefix from my peer. The state is up. If I do a show IP BGP, I should also see that prefix of 8.8.8.8. All right. Normally I would. I didn't do it this time, but I'm going to suggest something for you guys, especially for the lab exam. Make sure that you verify layer 2 reachability, layer 3 reachability before you start to go into actively configuring BGP. Okay? Always test basic IP connectivity before you start to get into maybe troubleshooting the BGP control plane, because we don't want to be troubleshooting BGP if there's some sort of basic TCP transport problem. Okay? Just something to keep in mind. Okay? I didn't do that. I would do a basic ping just to make sure I have reachability, but since I just configured these routers, I'm pretty confident that everything is configured correctly. So we got router 1 configured. Now we need to go in to do router 7. We're going to have an eBGP peering relationship with router 8 and an iBGP peering relationship with router 5. So let's do a show IP interface brief, exclude, unassign, and we're going to do router BGP 51, neighbor 172.16.78.8, remote AS 50, and we're also going to do a neighbor of 172.16.57.5, remote AS 50. Sorry, 51. This router 5 is in the same area as me. Okay, and lastly on router 5, I'm going to configure its relationship with not only router 5, or router 7, excuse me, but I'm also going to configure the peering relationship with router 4. All right, which means that we basically have everything done except for our iBGP speakers inside of AS100. All right, so let's go back to router 5. Show run pipe section BGP. Show IP interface brief, exclude, unassign, and config T router BGP. And this is going to be 51, neighbor 172.16.5 to 7, and that's going to be router 7. Remote AS is going to be 51, and let's do a neighbor of 172.16.45.4, remote AS 100. Okay. The 54 link we're actually not using. You can see that's shut down. That was what we had in our previous exercise. So I just have one more configuration here. Do show IP interface brief, include unassigned, exclude unassigned. All right. They're all assigned. All right. Router BGP 100, neighbor 172.16.45.5, remote AS 51. All right. Takes a little while for these relationships to come up. Not too much in this topology because we don't have a very large topology, but essentially now I should be seeing various relationships. If I do a show IP BGP summary, I can see that I do have an adjacency or a fully established TCP session with router 5. I'm not receiving any prefixes, which is interesting. That's the way it should be. And we'll talk about that in a little bit. Let me do a show IP BGP. Not receiving anything in the database. But now if I go over to router 7, do a show IP BGP summary, we are actually receiving a prefix from router 8. Okay. Now the question is that prefix going to get advertised over to router 5? I mean, they're neighbors, right? So if there is if I do a show IP BGP and I see that this is a valid route coming from 78.8 and it's coming from an eBGP peer, I should be advertising that prefix over to router 5. All right. Show IP BGP summary. And we do see that we are actually receiving that prefix from router 7. Show IP BGP. Shows that it's there, but we have a bit of a problem, right? There's essentially a couple of things that we're looking for here, and this is what the whole point of this discussion is, this iBGP relationship that we talk about. there are a couple of things that we're looking for here. All right. One of the most important aspects when you're looking at the BGP database is you want to see that greater than symbol, indicating that the route is actually usable. And when we add our iBGP mesh into this topology, we're going to have multiple ways of reaching different prefixes. We're going to choose one path over the other. We'll talk about what that decision process is. All right. The problem from router 5's perspective is it doesn't know who 78.8 is, right? 78.8 is router 8. Router 5 goes to router 7. This is a pretty typical behavior of an iBGP speaker, right? The next hop attribute, which was assigned by the eBGP peer that originated the prefix, is not modified when we re-advertise that route into iBGP. We actually talked about doing next hop self and other ways of kind of making sure that gets advertised appropriately. All right, we'll talk about that a little bit later on. I'm not going to fix it right now. I do want to do one more thing. I would like to originate some routes from router 7. So what I'm going to do is I'm also going to do a redistribute connected. So we're going to send some routes in from router 7. If I go over to router 5 now, show IP BGP, I see some routes listed here as well. And I did that for a particular reason because I wanted to demonstrate some of the concepts, AS path concept and rib failure concepts and so on. So we are seeing 7.7.7.7. Notice here the path indicates how the route was learned, right? The origin code. Was it learned through a network statement, which is what the little I means? The iGP means it was learned because we inserted that route into BGP using a network statement. That's why we see that for 8.8.8.8, because we use the network statement on router 8 to originate that route. Was it learned through some sort of redistribution process or maybe aggregation process? That's what the question mark indicates. So these routes are originated into BGP through some sort of redistribution or route aggregation process. All right, and if it comes from an external routing domain, you would see the AS path attribute here, meaning that the originator of that 8.8.8.8 prefix was in AS 50. All right. The redistribution of routes into BGP actually simplifies the next hop processing attributes that we will talk about later on in this lesson and in future lessons as we kind of get into more of our details of BGP. All right, we avoid problems of next hop processing by redistributing connected links into our domain. All right, we're also going to talk about what is the difference between using a network statement from a BGP perspective and using a redistribution process. Okay, so we know that we have our peers set up. We can see if I go into router 8, and I do a show IP BGP summary, I can see that I have two peers. I'm actually getting now 3 prefixes from router 7. I should also see all of the details of the prefixes if I do a show IP BGP. Any reason why 78 would have an R next to it? Right? We know that it's a valid route because it has a greater than symbol. Okay? And it's actually being advertised, 78 is being advertised from router 7 in this case. Router 7 is originating that route in area 51. And it's being originated through some sort of redistribution process. The reason why we have this little R here, it's called a rib failure. You can see that listed in the table here. R stands for rib failure. Is if I do a show IP route connected, we see that prefix listed as a connected route. So BGP says, you know what, I'm learning about this prefix through BGP, through the BGP process, because it was redistributed into BGP by router 7. But because I've learned this through the connected routing process, I'm going to ignore the BGP information and simply use the connected route. Which means I'm not going to insert this route into my rib, my global rib, because it's not going into my BGP rib. if that makes sense. All right. Like I said, there are a couple of fields to keep in mind here. The greater than symbol, that's the route we're using. And in our case, we actually, let me put this, well, it's right here. In our case, I'm not seeing a lowercase I. If I go to router 5, I can see a lowercase I next to each of these prefixes. That indicates that that was learned through an internal BGP process, iBGP peering relationship. It's very, very important that you guys can analyze this database, that you can look at it, and you understand how to read this information and interpret this information, because you're going to be using this information to do quite a bit of troubleshooting, not only on the written exam, where you're going to have to look at outputs and identify answers based on those outputs, but in the lab as well, particularly the diagnostic section and the troubleshooting section. Okay? We are going to talk about path selection options in BGP a little bit later on. That's going to be a completely different lesson. So let's now do some basic connectivity tests between the loopbacks on router 8 and router 7. I'll just do a quick ping to 7.7.7.7, and I'm going to source that from 8.8.8.8, and we have full reachability. It makes sense, right? We inserted the 8.8.8.8 prefix into BGP using a network statement. That's why it has a little I here for the origin. And we redistributed the 7.7.7.7 loopback. That's why we see the question mark here. So naturally, it means that we do have reachability between those networks that we're simulating. Okay. All right. Now let's go ahead and start setting up our other configurations, right? Like, say, for example, peering R1. Well, actually, you know what? I'm going to hold off on that for a second, right? We've already peered R1 with R8. We've already peered R5 with R7. And using the physical IP addresses. So if I go to R1, we'll just verify that peering. Show IP BGP summary. And we see that we have a peering with R8. And on R5, show IP BGP summary, we should see both peering relationships with R4 and R7. Okay. Now, in the case of convergence, you may see, for example, if you're in the process of configuring BGP, it's already been up for a little while, so we probably won't see this right now. But if you're in the process of configuring BGP, you might be looking at show IP BGP summary, and you won't see any prefixes, or you'll see if you do a show IP BGP, none of the routes will have a greater than symbol next to them. That just means that you're still waiting on the convergence process to complete. It just really depends on the timing when you're dealing with BGP. That's why a lot of times we don't really want to use the standard updates and withdrawal process that BGP includes because of the slowness. There are other techniques we can use in BGP to converge more quickly. Maybe we'll get into that stuff a little bit later on. Okay, but eventually we will see the greater than sign, and we just want to basically test reachability now to the physical IP addresses. So let's take a look at our topology here. Where's my snipping window? And kind of summarize what we've done at this point. We've got peering relationships between R8 and R1, R8 and R7, R7 and R5, and R4 and R5. Okay? Now, that means that there should be some reachability between, I'm trying to think about what's going to be able to see what. Certainly there would be reachability between these links here. There'd be reachability between those links there because they're connected. The question is, would R1 be able to reach, say, the loopback on R8? Or even would R1 be able to reach the loopback on R7? Let's take a look at R1's database. Show IP BGP. Oops. So I am getting 7.7.7.7. I'm of course getting 8.8.8.8, and I'm getting the link between router 5 and 7, and I'm getting the link between 7 and 8. My only concern, depending on how I source that traffic, is if I'll be able to reach the destination. And I don't think I will. Again, we've got essentially one-way reachability here, right? Router 1 is not advertising any prefixes into the BGP domain. Even though we have enabled BGP essentially on the link between router 1 and router 8, that doesn't necessarily mean that that IP address is going to be included in the BGP updates. Because again, we don't enable BGP on links, we enable BGP for routes. All right. We do have multiple exit points out of AS100. We have multiple egress paths out of AS100 to AS50 and 51. But we don't have any reachability, if you will, inside the domain. So even though I might be able to send a ping out to 7.7.7.7, router 7, if I do a show IP BGP, is not going to know how to go back to network 18. Network 18 is where that traffic would originate from. All right. So everything looks good so far. We've got basic connectivity between the external domains. Now we need to focus on how do we establish connectivity within AS100. All right. In our case, we're going to pretty much focus on doing a full mesh of iBGP. Like I said, we could use route reflection, we could use confederations, we could even do some sort of tunneling technique if I wanted AS100 to pass traffic through the domain, but I didn't want it to necessarily participate in the routing. But we assume in the case of IGPs that reachability is available for all the transmit segments. BGP doesn't work that way, right? If I'm looking at my topology here, if I was running some sort of iGP protocol within this AS100, and I was assuming, let's say I'm running eIGRP on all 4 routers, on all links on all 4 routers. I'm assuming in this case that link information is going to be included in that routing information. BGP is completely different, right? There's a clear disconnect between the NLRI origination in BGP and the actual routing to the actual prefix. So what this means in this case is if we're going to do some sort of full iBGP mesh, we still need to have some sort of underlying IGP transport in order to allow all the routers to form their BGP pairing relationship and then also complete the entire route recursion process, right? We go from our BGP recursion down to our IGP recursion, and we find our exit interface, we build our Ceph forwarding information base, and we do our forwarding, all right? So within AS100, what I'm going to do is I'm just going to go ahead and enable eIGRP on every interface, including the physical links and the loopbacks, and that will build out my routing domain for ASN 100. We're only going to do this on routers 1, 2, 3, and 4. Unfortunately, I can't really do it. I guess I could start it as a script here. Routers 1, that's weird. Why do I see router 1 twice? Router 1, 2, 3, and 4. And we're just going to do a and config t. Let's do router eIGRP CCIE. And we're going to do address IPv4, address family IPv4 AS1. And we're going to do a network of, I'm not going to do this very cleanly. I'm just going to kind of cheat a little bit so I don't have to go touch each of the routers. 172.16.0.0. That'll enable on all the links, the physical links. And then I'm just going to do a network of 0.0.0.0 with a wildcard of 3.255.255.255. Well, that won't work because that won't include router 4. Let me do it this way. Let's just do 1.1.1.1, 0.0.0.0, and network 2.2.2.2, 0.0.0.0. These are all the loopbacks. I know we don't have all these loopbacks on all the routers, but I'm kind of lazy. I don't want to touch all 4 routers. I wouldn't recommend this in the lab, of course. You want to make sure your configurations are concise. It's not really going to make much of a difference on the routers that don't actually have those loopbacks. So that should do it. Let's send that out. All right. Adjacencies, router 2. Adjacencies, router 3. Adjacencies, router 4 adjacencies. So if I do a show IP eIGRP database, I should show IP eIGRP topology, sorry. I should see all my loopbacks. There's 4, there's 1, there's 3, there's 2, and router 3 to 4, router 1 to 2, router 4 to 5. Even though this is an external link, we're still running that as part of our IGP. Router 2 to 4, router 1 to 8. This is also an external link. And we're obviously on router 4, there's equal cost ECMP is implemented to get to that particular link. So it looks like we're good to go. Okay. We've established our IGP routing path. All right. What I want to check now is if we can transit packets from the egress routers that are connected to our external peers. All right. Oops, Ken, sorry, I just saw your question online. Is that R because of a lower AD for the connected routes? Yes. So what you were asking about, sorry, I just saw that question. And I think I actually described the answer to you when I was discussing it. But yes, you're correct. When we were looking at the BGP database, there was an R to indicate a RIB failure. And that was based on the fact that there was another way we learned about that same prefix from another routing process that had a lower administrative distance value. In this case, it was a connected route with an AD of 0. So BGP says, hey, we're not going to go ahead and install that route into the BGP RIB. Okay. So let's make sure that we have some transit. We know that we will, but let's go ahead and test it anyway. Ping 1.1.1.1, and we're going to source that from loopback 0, and we have reachability. Okay. I could even do it to the external links as well. Ping 172.16.18.1, source 172.16.45.4, and I can ping between those links as well. So I've got full connectivity, full reachability through my IGP routing process in AS100, which means now I can start to consider how I'm going to overlay my BGP information on top of that. All right. The reason why this is very critical, it's based on the fact that BGP next hop attributes get reported into the network. All right, so let's assume that we have a route coming from R8 in AS50, and that's being learned through some sort of eBGP peering relationship. When router 1 advertises this into the iBGP domain, it's not going to change that next hop value. The next hop is going to be the link to router 8, which assumes we already have a route to that particular prefix. So looking at the topology, let me walk through what I just described. If I was looking at 8.8.8.8, which we know is part of BGP based on the network statement we implemented on router 8, there should be an 8.8.8.8 here. There we go. And there should be a 7777 over here. All right, so based on the fact that we have 8.8.8.8 implemented in the domain, that's going to get advertised through eBGP to router 1, and is it going to go to router 4? All right, now the answer in this case is no, but it will go to router 2 and router 3. Let's just check that real quick. If I go over to router 4, show IP BGP, and I do see 8.8.8.8, but it's coming in from router 5. Okay, it's not coming in, it's actually going through autonomous system number 50 where it's originating based on a network statement, and then it's going into AS51, and it's coming in as an eBGP route to router 4. but we're not learning it through iBGP. Now, if I go to router 2, show IP BGP. Oh, yes, we haven't implemented that yet. I'll show you guys that in a little bit. We're not running BGP on router 2 and router 3 yet, just router 4 and router 1. I don't think show IP BGP, yeah, not active. All right, I'm going to show you that, but I think you guys get it, right? We've seen this before. We can actually see this in the behavior from router 7 to router 5. Show IP BGP. 8.8.8.8 is coming from router 7, which is an internal peer, but it's identifying that destination as 78.8. Okay. Now it says I have reachability. Router 5 knows about 78.8, but that's because of the redistribute connected that we did in router 7. Before it didn't know, but when I did redistribute connected on router 7, it took that connected 78 link and it made it part of BGP. So we do have reachability. However, there is no reachability back to router 5, right? If I do a ping to 7.7.7.7 and I source that from loopback 0, it's not going to work because router 7 doesn't know how to get back to router 5's loopback. We're not advertising router 5's loopback into BGP. We'll have to do that eventually if we want to be able to test connectivity for the rest of the domain. All right. So when, as I said, when R1 advertises back into the iBGP domain, it doesn't change that next hop attribute. If BGP cannot ask IGP to do the route recursion, which is really important, that's why we set up eIGRP, then we're also not going to be able to have any reachability. In this case, there is some reachability because we did enable eIGRP on all the links in the domain. All right. So in this particular case, we're actually not going to have any issues with next hop processing. What I mean to say is that, let's say we did have BGP enabled on all of our routers here. Okay. And we had a iBGP pairing relationship between router 1 and router 4 in a full mesh. So if I set up a pairing relationship between router 1 and router 4, when 8.8.8.8 comes in, it will get advertised with the next hop attribute of 18.8 because that's the link. That's the link that we're establishing the eBGP pairing relationship on. That's the IP address we're establishing the eBGP pairing relationship on. In our topology, we're not going to have a problem with reachability because I went ahead and included this link in eIGRP. So BGP is going to recurse down to IGP to be able to reach the 18 subnet, and we'll have reachability, assuming based on whatever we're pinging from, and wondering whether or not whether or not we have the loopbacks or whatever we're sourcing our traffic from sent into BGP. Okay. So in this particular case, we won't have any issues, but just make sure you keep that in mind. We can do next hop self. That would fix that problem. I'll go ahead and set up next hop self. Actually, let's go ahead and do that on router 5 and router 7. So if I go to router 5 and I do a show IP BGP summary, show IP BGP, I can see that the 8.8.8.8 prefix that I'm learning from router 7 is originating that route to me, is showing a next hop of 78.8. We don't have a problem with this in this case because I'm sending 78.8 into the domain. But let's go ahead and go into router BGP 51 and let's do this. Let me go to router 4, router BGP 100, and I'm going to do a network of 4.4.4.4 with a mask of 255.255.255.255, which means now router 5 should be getting a prefix from router 4. Do show IP BGP summary, right? So we're getting a prefix from router 4, and if I do a show IP BGP, the next hop attribute should be the 45.4 address, which is the link that router 5 is paired with, the interface that router 5 is paired with. All right. Now, if I go to router 7, show IP BGP summary, I can see that I am getting that prefix from router 5, but if I do a show IP BGP, the next hop attribute is 45.4, and it is originated through internal internal BGP right here. So these are grouped together for a reason, right? Because these are the 3 characters that would show up next to your prefixes listed in your database. All right. But we notice that it's not a valid route. It's not being inserted as a route, and that's because router 7 doesn't know how to reach 45.4. I didn't do redistribute connected. I didn't send the 45 link into BGP. So what I could do in the case of router 5 is I could say neighbor 172.16.57.7 next hop self. I guess it would help if I was in the BGP process. Router BGP 51. Neighbor, let's do this. Next hop self. There we go. All right. So you'll notice on router 7 now, if I refresh this database, I can see, let me do a clear IP BGP star in. That will just say, hey, can you please provide me a refresh of the routing update information. And I will see now that this route is a valid route because I know how to reach 57.7. Okay, 57.7 is an internal peer. By the way, it's a connected route as well. That's why we have a next hop of quad zeros indicating that that is a self-originated route in BGP. And that's self-originated because we're doing redistribution. Normally I wouldn't see the 57 network in this database because I normally wouldn't include my transit links into BGP. We're doing this in this case because just trying to demonstrate a couple of different options here. Some of these concepts we talked about in our last lesson. Doesn't hurt to see them again though. Okay, so these are all eBGP routes. We can tell that because there's no I. They're all valid routes, redistributed, originated through a network statement, coming from another autonomous system, redistributed from a network originated from a redistribution statement within our own autonomous system, and that's also indicated there that we're originating that route individually. Okay, so we can go ahead and establish the rest of our peering relationships. Let's go ahead and do that. I was going to do this individually on each router, but I think what I'd rather do is just kind of go in and do kind of a peer group and get all these routers configured at once. Because I was going to do router 2 and router 1. Basically what I want to do is I want to go in and complete this full mesh here between router 1, router 2, router 3, and router 4. I could go in individually and do all my neighbor statements, my remote AS, my update source if I wanted to, because I'm essentially duplicating the configuration for 3 different peers on each of these routers. It's going to be probably a little bit easier for me to go ahead and just use a peer group, and that will reduce the number of configurations that I have to have. So what I'm going to do is let's go into Notepad here. And let's do this. Config T. Let's do neighbor. iBGP mesh peer group. So we're going to set up a peer group. And we'll go ahead and say remote AS 100. And we're going to say update source, update dash source, I believe it is, loopback 0, and then I'm just going to go ahead and put in my neighbors. 1.1.1.1, let's assign this to peer group, iBGP mesh, neighbor 2.2.2.2, peer group, iBGP mesh, neighbor 3.3.3.3, peer group, iBGP mesh, and neighbor 4.4.4.4, peer group, iBGP mesh. Now, obviously, I wouldn't want to include myself in my neighbor statements, but in this particular case, all it's going to do is say, hey, I can't peer to myself. It just makes it, it's not clean, but it makes it easier to add all the routers into the topology. So the parser is going to give us some sort of warning. We're going to go ahead and ignore that warning and just get the rest of the configuration done. All right. And we might as well do a write at the end of that as well. So let's copy this. All right. Actually, there is one other thing I want to do.
You need the BGP command too, right? The router BGP.
Oh yeah, that would help, definitely. Thank you. All right. I was thinking about the other thing I might want to do too is include the loopbacks network. Because eventually we're going to want to have some sort of reachability between these platforms. We don't necessarily care about the transit links, but I do want to be able to reach the loopbacks. If I have to take some of this out later, I will, but all right. So let's go into our configuration here. 1, 2, 3, 4. Paste that in. Let me do an end at the top here because we may still be in config mode. All right. Got 2 ends. That's okay. All right. Got our neighbor. So now if I do a show, show run pipe section BGP, it should have ignored a lot of the other stuff. I mean, the network statements are going to go in there regardless. Doesn't really make a difference in this case because only 1.1.1.1 is going to matter. BGP is only going to insert routes into the rib based on matching some sort of specific route in my global rib on the router anyway. But I should be able to now see the different show IP BGP summary, the different peering relationships I have with the different routers. Getting 7 prefixes from router 4, 0 prefixes from router 3, 0 prefixes from router 2, which makes sense, right? I shouldn't get any prefixes from router 2 or router 3 unless they're originating them. Actually, most likely, if I do a show IP BGP, I do see that I'm actually getting prefixes from router 2, but we're not using any of them. We're using show IP route. I should be seeing some rib failures for those prefixes. For 2.2.2.2, might have to wait a little bit. Because 2.2.2.2 is originating inside of our iBGP domain from router 2, that's the loopback. So it's definitely going into the database on router 1, but it's not being put into the BGP rib because we're learning about that same prefix through EIGRP. And iBGP has an administrative distance of 200, whereas eIGRP has an administrative distance of 90. All right. We'll get into some of that, but we're going to go ahead and look at, notice we do have several different ways of reaching destinations now, but we're going to kind of analyze this and talk a little bit about the path selection process and you know, kind of play around with some of the settings and see how we can manipulate this a little bit. Okay. The key point of update source, right? And that was part of my template configuration that I had with BGP. The key point of update source is that when BGP binds the application as a socket, it has to agree on what the source and destination is going to be for the TCP client and server relationship. We talked about that in our previous lesson. All right, if we don't bind it to that particular source and it's coming from, say, the exit interface or egress interface on the source router, it's going to deny it, it's going to send a TCP reset and so on. All right, we would assume, of course, that we would change this on both ends so that we could establish the peering relationship. All right, now if I focus on router 2, for example, I should see now router 2 has multiple exit points to reach an external prefix like 8.8.8.8. Show IP BGP. Specifically 8.8.8.8. Actually, we're not seeing that here. Let me make sure. Show IP BGP. 8.8.8.8 here. So we are seeing the multiple exit points from router 5's perspective. It can either go to router 4 or it can go to router 8. It's choosing the path to router 8. We didn't do the next hop self on router 8, or excuse me, router 7 to change the next hop attribute, which is why router 2 is not seeing that from that perspective. But let's go to router 4 real quick. And for 8.8.8.8, we see two options. That's what we should see. I can either go to router 8 within my iBGP domain, or I can go over to AS51, then to AS50 through router 5. I'm choosing to go to router through my iBGP domain to 172.16.18.8 in this case. We'll play around with this. We'll see if this is optimal, if this is the best choice. In this case, it happens to be the best choice. And it is our primary choice based on the BGP selection process. One of the primary BGP selection processes that we use is AS path. And the shorter AS path is always going to be preferred over the longest AS path, regardless of whether or not the route originates inside of my internal BGP domain or externally from an external BGP peer. This AS path 50 is shorter than 5150. We could do AS path prepending if we wanted to maybe force a route to take a different path. We can also apply some weights to the external routes. I'll show you guys how to do that in a little bit, to prefer the external routes over the internal routes. But right now, router 4 is preferring the internal route to reach that particular destination. All right, but we do have multiple paths to the external network. Specifically from an iBGP full mesh point of view, this is actually the advantage of the design because it gives us path diversity. All BGP peers are learning about all the different egress paths that are available because we're directly peering with everybody within the AS. All right, what this means from a traffic forwarding point of view is that the result is always going to be whatever the optimal egress for the traffic flow itself. The path selection by default is going to be basically based on an IGP metric to whatever the egress router is. We'd have to look at this from a different topology standpoint because we don't have the right kind of topology to demonstrate that particular concept, but router 2 should show IP BGP. router 2 is making a decision to go to 18.8. I'm curious why router 2 is not receiving this prefix from router 4 though, because it is an iBGP peer with router 4, and router 4, oh, I know why. I know why. In BGP, routers are only going to advertise essentially the prefix or the path that they're using. Right now, even though router 4 knows that it can go to 45.5, because it's choosing to go to 18.8, that's the path it's advertising. So that's what router 2 is going to see from from router 4. So say, well, I'm already going to 18.8 anyway to reach that particular destination, so I don't need that information. Okay. Now, if I look at, say, some of the other prefixes like router 1, for example, the 1.1.1, I'm going to be receiving this prefix from all three of my peers. I'm going to receive it from router 3, I'm going to receive it from router 4, and I'm going to receive it from router 1. But I'm actually choosing the path directly to router 1 in this particular case because of the connected link. Again, that's my preferred path. These are paths that are being learned through iBGP. This path is not being learned through iBGP. It's actually being learned directly from the peer, from that advertising router. So it looks a little confusing because we're actually looking at this as a topology database essentially, where we're able to identify how we're learning about each of the prefixes, who we're learning them from. But we have to go through the path selection process to truly understand how BGP is making its decision. All right. Now that concept I described before, where all the peers learn all the paths out of the network, meaning that we know how to reach the destination based on the closest egress path, that's called hot potato routing. Once the packet enters the network, we want to get it out of the network as quickly as possible. All right. And I'm still not seeing, there's some interesting things happening here that I need to figure out. Let's take, for example, this 78 link. The 78 link is being advertised by router 7 because of the redistribute connected. So it's being originated by router 7. But it is not being originated by router 8 because we didn't have an option. We didn't have any kind of network statement for the 78 prefix. Let's go ahead and add that into router 8 and see. There's one thing I wanted to show you guys. (172.16.78.0) mask 255.255.255.0. All right. Now if I go to router 2, I should eventually see what was already coming from. It was already coming from 8. I think I know why. Let's do this. Neighbor. Sorry, it'll be 172.16. 57.5. What I'm trying to see is why 78.8 is not showing up with multiple options. Because R2, let's look at the topology diagram. R2 should be learning about the 78 prefix from originating from router 8 and from router 7, because router 7 redistributed connected into BGP. Now, just because we're using one route versus the other, that's based on the BGP path selection process. The origin code is one of those choices in the path selection process. Where does the route originate from? But I'm just curious why we're not seeing that prefix. It has to do with R5. Let's go to R5 real quick. So R5 is learning about it. So it's definitely getting into AS100. There's 78 in AS100, and we're getting it from router 7. I'm just curious why router 2 is not seeing that from router 4. I know why. When it gets from router 4 into the iBGP domain, it's not... Let me think about this. I was just trying to figure that out. It's kind of annoying. All right. Anyway, hot potato routing is the concept that I'm going to try and route the packet as quickly through the autonomous system as possible using the quickest egress point to the network. And I should be aware of what all the egress points are, and then I can simply rely on my IGP to make a decision as to how to route to the closest egress point from that domain. Cold potato routing would be a situation where you have like route reflectors, or you're doing some sort of control plane scaling, and you're not necessarily choosing an optimal path, but you're choosing a path based on configurations of confederations or route reflectors and so on. There's actually several documents out there. If you search cold potato routing or hot potato routing or mashed potato routing, believe it or not, that's a term, which describes kind of a combination. There's actually ways that we define how that takes place. All right. So we have all the peerings now configured with all the routers. We know all the egress points in the network, and each router now gets to make its own independent decision on how to lead the AS. That is one of the things that is working correctly. Looking from the perspective of router 2 versus, say, router 3. If I do a show iBGP on router 3, I can see that for these routers, for the most part, we're pretty much making the same decision, right? Go to router 2, show iBGP, well, it's right here. I can see that for the 57 prefix, I'm going to router 4. For the 78 prefix, I'm going to router 1. I added the next top self to the edge routers on the ingress on the iBGP domain so that we could see the router IDs. But I'm going to router 1 in this case. From router 2's perspective, well, the same thing is happening here. So from router 3's perspective, I'm going to router 1. And if I look at, say, for example, the edge routers, they're going to have a different view of the topology. Show iBGP, clearly, because they have different attachment points to the network. We're going to use 18 on 8 to reach the 78 subnet. This is another example. We have two ways of reaching the 57 subnet. We can either go to router 8 through eBGP, or we can go to router 4 through iBGP. In this case, we chose to go to router 4. Why? We chose to go to router 4 because of the AS path attribute. 51 is shorter than 50 and 51. That makes sense. All right. We haven't discussed the BGP path selection process yet. That's a very, very important topic. Something we'll definitely talk about a little bit later on. All right. Assuming everything is equal within the IGP domain, everybody really should make the same agreement on how to route to the egress routers, but iBGP doesn't have that same concept, right? It also doesn't have much for loop prevention built in. There could be loops in certain designs. In our case, we know there's not a loop because we are relying on our IGP protocol to essentially eliminate those loops, right? eIGRP is using feasibility condition checks and whatnot to identify whether or not there are loops in the eIGRP topology. All right, so we did our templates. We're going to use templates for a lot of other configurations later on. All the routers are now running BGP. and we have internal peering relationships with all the routers. Again, if I go into router 1, for example, and I do a show IP BGP summary, I will notice that I'm receiving prefixes from router 2 and router 3. Okay, but I'm not, if I go to router 2, show IP BGP summary, yeah, now we're seeing all of our prefixes. We were seeing zeros there before because in the case of BGP, it takes a while for it to converge. I would potentially see zeros there even though I have adjacencies, and that's because certain iBGP peers are not going to advertise other iBGP routes to those peers. In our topology, because we have a full mesh and all the prefixes are coming from external domains, we're going to be getting prefixes from all of our peers. All right, that's again that loop prevention mechanism. We're actually technically only getting prefixes from the edge routers in this case. It's just because because of our topology, our physical design, we're seeing that we're getting prefixes from internal peers, even though they're not technically internal routes, right? They're external routes coming from our external domain. I can also see if I want to see what I'm advertising to my peers. This is a helpful command for troubleshooting. I can do a show IP BGP neighbor. Let's do 3.3.3.3 advertised routes. And I can see what prefixes I'm sending to that particular peer. So I can see I'm sending 1.1.1.1, 2.2.2.2, 3.3.3.3, and 4.4.4.4. Right? Those are the prefixes that are originating inside the domain. All right, but they're originating from that particular router, right? So we have 4 prefixes originating from this router. 1.1.1.1, the next hop is 12.1, which is router 1. 2.2.2.2 is self-originated. 3.3.3.3 is coming from router 4. And 4.4.4.4 is coming from router 4 as well. All right. Which is actually interesting. What I had done previously when I set up BGP originally, I added network statements for all of the loopbacks. And yeah, those are received routes, excuse me. Well, there's also received routes, yes. You can do advertised routes or you can do received routes. Sorry, that was a question online. The reason why, this is why also it's important to understand how to read this database, right? Because I'm thinking as I'm describing this, there's really no reason why router 2 should be originating quad 3 and quad 4, because those should be routes coming from another iBGP speaker, and that breaks the propagation rules, right? Saying, hey, I'm not going to advertise routes I learned from another iBGP peer. But I added network statements on every router. I should have only done it on the perimeter routers. I actually did it on all the routers. I added network statements on all the routers for the loopbacks, which means that they're now being advertised outside of the autonomous system. They're being advertised out of AS 100 into AS 51 and 50. So they're actually coming in as external routes. I'm just not sure. Well, I probably shouldn't have included those. We're not seeing AS path information though. So something weird is happening here. Let's clean this up a little bit. We're almost done, guys. Hang on there. Let me clear this up a little bit. Router BGP 100, no. Let's get rid of all of these. Oops, this wrong one. And let's do We're kind of piecemealing this network together here. Obviously, we'd probably come up with more defined approach to actually advertising prefixes in the end. And we of course would only need to advertise prefixes that would allow the AS to transit traffic. So actually, in reality, if you look at the topology diagram, if I'm assuming that I'm adjusting the next top values on the egress routers to their local loopbacks, I would really only need to make sure that this loopback and this loopback are part of the routing process. So let's actually clean this up a little bit. Let's take out all the loopbacks, because I don't even need to put these into BGP in order for reachability, you know, through this AS to go from, say, R8 over to R7. If I were to shut this link down, we want to be able to make sure that these R7 networks are being propagated through BGP. They're being sent through our iBGP relationship, and then they're propagated over here, but I still need reachability. I don't need it, the detailed, I would never really advertise the details of my autonomous system to other routers outside of my autonomous system anyway. So let's actually do that in all these guys here. So let's go in here. No, 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 no. And copy that. That's good. So now if I look at what I'm advertising from router 2's perspective, I really shouldn't be advertising anything to router 3. Right. Okay, that makes more sense. Because again, router 2 and router 3 are iBGP peers, and router 2 is going to learn about eBGP routes from router 4 and router 1. It's not going to re-advertise those to router 3. All right, now the question is, do we still have routes? So if I do a show IP BGP, we still have prefixes. All of our external prefixes are in the list here. We don't see any of our internal prefixes. Now, do I have reachability? In order for me to have reachability, some things would have to be advertised, especially if I'm going to route my loopbacks. So let's say, for example, on router 2, I wanted to be able to ping 8.8.8.8 from my loopback. I would have to advertise this loopback into BGP because it's going to have to be sent out of the domain. So there's a couple of ways I can do this. Maybe perhaps one of the cleaner ways of doing this would be to do this on the perimeter routers and just say, okay, take all the loopbacks from eIGRP and let's go ahead and send those into BGP so that they can be routed, or those prefixes can be sent out to the rest of the network. Let's actually do that. So we're going to come in, we're going to create a access list. IP access dash list standard loop, and we're going to do a permit host 4.4.4. Let's do 1.1.1.1 permit host 2.2.2.2 permit host 3.3.3.3. We could probably just leave off the host. It would just assume it's a host, but 4.4.4.4. And let's put that into each of the routers. All right. So I'm creating an access list to match all of my loopback addresses. We'll send that in. All right. And then what we're going to do is we're going to do a router BGP 100. We're only going to do this on the perimeter routers. Where is my notes here? Router, BGP. Well, let's do a route map first. Route map. Redis loop. Match IP address loop. And then finally router BGP 100 redistribute eIGRP 100. I think I'm using 100. Let me see. To show IP protocols. eIGRP 1. Okay. Route map redis loop. All right. And we need to do this on both the routers. So in this case, we're just going to send in those loopbacks on our perimeter routers, which is router 1 and router 4 into BGP. And hopefully that will fix our problem. Send that in. Assuming I didn't make a mistake on. So router 1. Didn't paste router 1. Did I pick the wrong router? Oh well, let's just copy it. All right, so show IP BGP. I should see now those loopbacks with a question mark. There they are, indicating that they're coming in through a redistribution process. And I should be able to go to router 8, show IP BGP, and I should see those loopbacks here. And I'm seeing them from 2 different places. Perfect. All right, so I'm seeing them from router 7, and I'm seeing them from router 1, 18.1. We see the AS path there. I'm choosing the path through 18.1 because of the AS path, but these are external routes, not internal routes. So I should now be able to ping, say, for example, 2.2.2.2 with a source of 8.8.8.8. Perfect. Okay. A little bit cleaner. The point here is there's actually a couple points I want to make here. Sorry it's taking so long, guys. This is kind of a long one. All right. A couple of points I'm trying to make here. We don't need to necessarily know about the transit paths in AS100 because we're relying on our underlying IGP for reachability within AS100 between the iBGP peers. So I'm just putting in some loopbacks here for connectivity, for testing. Maybe these are prefixes that I'm advertising out to the rest of the internet or whatever. But I didn't need to originate those prefixes from every single router within the domain. We're already creating reachability to those prefixes in the domain using our IGP. I just need to be able to advertise those prefixes to my eBGP peers, which only needed to happen on router 1 and router 4. Okay? Hopefully that makes a little bit more sense. All right? If I look at router 8, I see all the routes. We can do our connectivity tests now. I should be able to really pretty much have connectivity to everything. Let me try the TCL script here, and then I'll do it. Yeah, maybe one's not going to work. Well, we know essentially that we're going to have connectivity, right? If I ping, for example, if I come over to router 7 and do a ping to 2.2.2.2, source that from 7.7.7.7, I'll have reachability. I don't know if I have the loopback on router 5. Let's try 3.3.3.3, source 5.5.5.5. Yeah, I'm not sending 5 in. But anyway, we do have most of the reachability that we need. All right. Just keep in mind, and this is really what I wanted to demonstrate, from the perspective of BGP, connectivity testing is a lot different than IGPs. We're not going to assume that someone external to our AS is going to be able to ping any of our transit links, because our AS, in most design cases, we're not going to be advertising those transit links to other individuals. Okay? IGP routing is used to build reachability between infrastructure links. BGP is used to build end-to-end reachability between where the application segments live. All right? And that's where the decision process comes into play. Just keep that in mind as you're doing your troubleshooting. Okay? So let's start on router 1, and we're almost done here. We're just about to wrap up, but I just want to take a look at the decision process that router 1 is making versus router 4 on how to reach some of these external prefixes. If I go into router 1 and I do a show IP BGP, we want to look at the external ones. If I do a show IP BGP, I'm going to see a whole bunch of internal ones as well. Let's do a show IP BGP. This is kind of cool. I'm going to use a regular expression, and essentially, let me see, probably take longer to do this than just looking at the table. Let's see if that works. Yeah, perfect. Okay, so what I did is I used a regular expression in this case to parse the output. I'm asking the router essentially to show me the routes that have at least one AS path listed in the route. So anything that begins with 0 through 9 plus additional characters, and I'm looking for specifically values in the path attribute. And there's a whole bunch of different filters that you can apply. We'll probably get into looking at some other filters a little bit later on. But basically, I just filtered out all of these internal routes. I mean, I didn't save a whole lot of time in this case. Could have easily seen that on that table above. But imagine if you're doing this for a table that has millions of routes or hundreds of thousands of routes. That's where you have to consider, maybe using some of these filters to make your life a little bit easier. All right. So we'll talk more about some regular expressions a little bit later on. Right now, I'm basically just saying, show me all my non-local routes. Basically, the local routes would just have a null as a path or no numbers in that particular list. Show me a path that starts with at least one AS, because if I know if it has an AS, it's not originating from me. All right. So if we look at this from the comparison of router 4 and router 1, we'll do the same output or the same command on router 1 or router 4. We can see that the decision process is slightly different, right? For 7.7.7.7, router 4 is choosing to go to router 5. Router 1 is choosing to go to router 8. Actually, router 1 is actually choosing to go to router 4. It's choosing the same path, actually, which makes sense. It's a shorter AS path. For 8.8.8.8, router 1 is choosing to go to router 8. Router 4, of course, should be choosing to go to router 8 as well, because, again, it's the shorter AS path, router 1. All right? So we can see the decision process here is pretty detailed. I mean, it's not detailed, but it's pretty accurate, right? We're trying to make decisions on how to route to these external domains based on the BGP path selection process. The topologies might, the decision might actually look different. It doesn't in this particular case, but if our design was a little bit more complicated, we had multiple egress points and lots of different places where we could route, we could potentially see different ways or different decisions on how routing is being made. Which one I choose determines on what's actually being advertised by the peers. My point is that the topology doesn't always have to be the same. All right. So based on AS path link, we're going to choose the closest AS in this particular case. That may not actually be the most optimal path, right? We may actually choose to go to a different path based on path metrics and so on. BGP doesn't have that capability. All right. With a full mesh of iBGP peers, we're always going to choose the closest egress location based on the IGP routing process. All right. Now, if I look at This is the last thing I'm going to show you guys, I promise. On router 4 for 8.8.8.8, I'm preferring the internal path over the external path. So I'm actually using essentially my AS as a transit to get to that external network, even though I could go to an eBGP peer to get to that destination. What if I didn't want that to happen? What if I wanted, say, to only use my external paths to reach those external destinations? I don't want to go through my AS to get to those external destinations. There's actually a way we could do this. We can go into router 1 and router 4, which are edge routers, and we can apply another attribute called the weight attribute, router BGP 100, neighbor 172.16. This is, we're doing to router 8, and I'm going to say apply a weight of 1 to all those external paths. Okay, the higher value is preferred. The default is 0, so just setting it to 1 is going to result in that being more of a preferred path. Neighbor, in this case, it's router 4 to 5, 172.16.45.45.5, weight 1. All right. Now, if I do a show iBGP, I should see, let me do a clear iBGP star in so that I can apply updates to my, or apply my policy to the new update. Clear iBGP star in, do show iBGP. And I should see, in this case, let's do this. Well, you can see it here, right? Now, every one of these external paths are getting a weight applied to them of 1. All right? Which means that for this prefix, even though the path through router 4 has a shorter AS path attribute, we're going to use weight as our deciding factor to egress or to leave the AS. We'll talk more about the BGP path selection process. Weight happens to be it's a Cisco proprietary attribute that happens to be at the top of the list. AS path, I think, is the 3rd or the 4th in the list. So weight is going to win. All right. It's all about manipulating how BGP decides it's going to route. All right. What are the disadvantages of having a full mesh? Like I said, the main problem is data control plane scaling. A full mesh means that we're going to have n times n to the n minus 1 divided by 2 number of peerings. And for a small number of routers, that's not a big deal, right? 10 routers, maybe we have 45 peerings. But if you go up to 100 routers, now you're looking at 4,950 peerings. If you go to 500 routers, it's like 124,000 something peerings. Operationally, it's also very hard to scale. Adding or changing the peering configurations, that's kind of administratively prohibitive because of all the number of peers that you have to have and so on. We will talk more about this later with regard to using route reflection. I will reference a document that maybe you guys should take a look at before we get into that discussion later on, where we have an alternative to doing a full mesh, which is in the actual route reflector RFC, BGP route reflector RFC. It's RFC 4456, an alternative to full mesh BGP. Specifically in section 11, they state that one of the key components of route reflection is to address the scaling issues that route reflection summarizes routing information and only reflects the best path. But there's always a trade-off, right? There's a trade-off between control plane load, which you would have in a full mesh, versus actual NLRI information and detail. All right, it's always going to be kind of a give and take. All right, so we'll actually see some examples in some of our future lessons where we kind of mix up both of those. Okay. All right, guys, sorry for keeping you so long today. I knew that this was going to be a long one. Most of our BGP discussions are fairly lengthy. Hopefully you got something out of this session? You guys have any questions, any comments, concerns? Winning lottery numbers, anything? Okay. All right. Well, looks like we'll probably have another session this weekend, most likely on Saturday. I'll send you guys a Slack message and we'll figure out what time that's going to be. But thanks for sticking it out with me today, guys. Especially you, Chris. I know it's way past your bedtime. All right. See you guys in the next lesson.